Was he even born on that photo?
Yeah.
The next talk will be by Ashutosh on the topic criticality of AC0 formula.
Okay, hi everyone. Thanks for coming to the evening session. I'll be talking about criticality of AC0 formulae. This work was with Prahladh and Tulasi, and it was presented in CGT. So let's start with, we've seen a few Boolean functions today. So I'll be a bit loose, maybe talking about functions versus families of functions, but I think you will know. So there are three ways of computing Boolean functions that will be characters in this story today. So the first is formula. We saw it in the morning. So it is a rooted tree where the leaves are inputs, the other internal nodes and the root will be gates, and the final root, what you get is the output. So we'll assume that there's only ands and alls and all negations and stuff like this. So this is a formula. A circuit is similar to a formula, except that it's not a tree, it's a DAG. So you can reuse some computation, so it's possibly less wasteful than one that's slightly different is a decision tree. So the decision tree is you query one variable at a time and you keep branching, and then once you are able to deduce the value of the function, you say whatever it is. So all of these essentially tell us information about how simple or not simple the function itself is. And there are various parameters that we'll be interested in. So for formulas and circuits, we're interested in the size and also the depth. And for decision tree, we're interested in just the depth. So what can we do with these things? So I'll explain one keyword in the title at a time. So AC0 circuits and AC0 formulae are basically for like I said, families of functions, sometimes that have growing numbers of inputs, right? For instance, majority on n is a family of functions for every n. So if you can compute the family of functions with just constant depth, then we say that the circuits or those circuits or those formulae are in AC0. So here's an example of both a circuit and a formula with depth 2. So a depth 1 circuit or formula is just a singular and or an or with variables and maybe their negations. With depth 2, you can do CNFs and DNFs. And you can, of course, move between, you can convert a circuit to a formula by whatever the redundant computation that you've been doing, you have to make copies of those. So in general, that makes the size go from S to B. So here's one function or other family of functions that we will be looking at a lot today, and that's the parity function. So the parity of n bits is the parity of the number of ones. So circular definition maybe, but it's 1 if there's an odd number of ones in the input, and it is 0 if the number of ones in the input is even. So the reason why this is interesting is that on the face of it, there doesn't seem to be an easy way to do it with just ands and ons, right? You sort of need to read every bit and like keep the count in your mind when you're computing the parity. So that's why this is a natural thing to consider for something that might be hard with just a small number of ands and ons. So so there, like I said, there are actually size bounds for how much you can do this with small depth. So with just a single and or an or, you can't compute parity. If you're allowed to do CNFs and DNFs, you have this sort of exponentially large thing to the n minus 1. If you're allowed depth 3, you can do it in 2 to the O of root n. If you're wondering how, it's like this. So you make the n variables into root n groups of root n each. You do the parity of each of those with the CNF and DNF, and then you smash the middle layers together and get a depth 3. In general, if you're allowed depth d plus 1, you get this 2 to the O n to the 1 by d. And in the general case, this is where you see the difference between circuits and formulae. So depth 2 and 3, they look the same, but over here there is a d that comes in when you go from circuits to formulae. So, okay, bottom line is parity seems to be difficult to do with small size circuits of also small depth and also formulae. Here's another character, which is random restrictions. So this is another way of ascertaining what happens to a Boolean function when you do something. And this, yeah, it tells us information about how simple or how complicated the Boolean function is. So how you apply a random restriction is like this. You take some p between 0 and 1, p for probability. And for each variable, x1 to xn, you independently do the following. So with probability p, you do nothing. You leave it as star. So now with the probability 1 minus p, you do the other thing, which is with equal probability half and half, you set it to 0 or set it to 1. So for each variable, you look at it with probability p, leave it. With probability 1 minus p by 2, set it to 1. Probability 1 minus p by 2, set it to 0. So you get a resulting function, right, on typically a fewer number of variables. So we'll call this resulting function f restricted to rho. So this whole restriction that we're doing is called rho. So f restricted to rho. So our thing that we're trying to do is what happens to different types of functions when we do this. And one major statement about this, very classical, very celebrated, is called the switching lemma. So the early statements of this type were by these people in the 80s, Sachs, Sipser, Aitai, Yao. And yeah, the reason it was originally called switching lemma is that they said how to, it was going between DNFs and CNFs. So switching between DNFs and CNFs and switching. But that's not the way that we usually write it down. We usually write it in terms of something else. So the version that we usually see and talk about is Harsha's switching lemma from 1986. And this is the statement. So if f is a k DNF, forget about AC0 and alpha now. F is a k DNF. K DNF means each term has k litters. We don't care about the number of terms. We don't care about the number of variables. So k DNF. Then for any t, this what's going on here? Let's see this from inside out. So first you apply the restriction to get f restricted to. Now this is just some Boolean function. It has some decision tree, some optimal decision tree, and we ask what's the depth of this. So the probability that this has, and yeah, the depth is a random variable, right? Because the restriction is a random. So the probability that this depth is at least t is at most this 5 times p times k whole to the power p. So for instance, the probability that the depth is at least 1, if it doesn't just become a constant, this just 5 times p times k. This is quite a remarkable statement. Just if you haven't seen it before, just take a second to see why it's so interesting. Because there's no mention of the number of variables. There's no n here. There's no mention of the number of terms or anything. It just depends on the width, which is it's pretty nice. So this is for DNFs. So this is what happens when you apply a random restriction to a k DNF. The decision tree depth of whatever results is unlikely to be large. That is the switching lemma. Now, even though the switching lemma is a statement about DNFs, it actually gives statements about the power of AC0 circuits. So how is this? So think about parity, the parity function, applying a random restriction to. Now, this doesn't really help in simplifying parity, because even if you set a bunch of variables, whatever is left, you still have to basically find the parity of the entire thing. Right? So parity doesn't simplify much under random restrictions. Whereas you can, with not too much difficulty, using the switching lemma, you can find structural results about AC0 circuits, or rather functions computed by AC0 circuits. Once you apply random restrictions, what happens? So using this sort of comparison, that hitting parity with random restrictions doesn't do very much, whereas hitting these AC0 kind of formulas with random restrictions does simplify. So because of this difference, we see we get the result that small sized, small depth circuits will not be able to compute parity. So if you want, if you require the circuit to have small depths, then it will end up having this large size. There's another nice consequence of switching lemma that isn't kind of tangential to this talk, which is a Fourier concentration. So if you know what Fourier coefficients are, this one basically says that most of the mass of the Fourier coefficients lives on the smallest. So mass that lives on the larger sets is. So very nice. So this switching lemma has given us a size bound for AC0 circuits for parity. You can see some more rows and columns here. So what happens with formula? So you can ask Rossman, and he has found as a corollary of the switching lemma that you have a size bound for formulas computing parity, and the size bound looks like this. So if you remember, the circuit thing was 2, and there was an end to the 1 by d here. For formulas, there's another little d introduced here. Good. So we have one row completed, which is size bounds for circuits and formulas against parity, just coming from the switching lemma. So what's this other row here? So we have seen that like small size circuits don't do very well computing or whatever, or rather they cannot compute parity exactly on all inputs. So now you might ask, can they at least compute something similar to parity? Can they compute something that is highly correlated with parity? You can guess the answer is no. So the way this is formulated is in terms of correlation bounds. So how well do AC0 circuits and formulae at least correlate with parity? Are they similar to parity? So correlation is defined like this. So between two Boolean functions, the fraction on which they agree minus the fraction on which they disagree. This is correlation. So in our case, one of them will be parity, and the other one is some function that you know has a AC0 circuit or formula. So the question was first posed by Rahul. It's interesting in its own right, I think, but also it turns out to give theorems in structural complexities. I think it was used to also prove a random oracle separation between P space and PH. So these people gave some these correlation bounds against parity. BV impact Srinivasan, impact Matthews per 2B. But here is a pretty much optimal correlation bound, the return of the king, Hastad again. So he said that if f is a function that is computed by some AC0 circuit, depth is d plus 1, size is s, then this correlation is this exponentially small. So exponential n minus n by log s to the d. So this is what we have. So a bit of a detour now. So for the final keyword in the title, what is criticality of a Boolean? So the definition is due to Rossman, and so if f is some function, then the criticality lambda is basically what you if you were to write a switching lemma kind of statement for this arbitrary f, what you get on the right side paired with p. So if you remember the switching lemma, it was this for DNFs, and over there was a 5 times W times P. So the P is inevitable there. So whatever also is over there, that is, so to put it simply, that is what we are calling as criticality. So the criticality for, so this is criticality for a single function. For a class of functions, for example, DNFs, the criticality is 5 times.
Smallest. Yeah.
Smallest. I didn't make this statement.
So can you put the slide about formula size?
Oh, that was the very big
Yeah.
For parity.
For parity. Yes. Yeah. So is the D there essential?
This is a lower bound. So.
Yeah. But I'm asking what about upper bound? I mean, we know that like circuits we do not have the D. Like, is there a circuit for AC0? That was the slide.
The upper bound basically had omega replace the dot.
I see. Oh, so these are type. These are type up to the constants given as the omega. Okay.
Yeah, if you have, I mean, for the people with some free time, if you want to try drawing parity like circuits and formula, you can do that. Spend some time on that, and you start seeing the difference if you like 5 bits, 6 bits. Then you start seeing that formulas and circuits look noticeably different. 4 and all they look the same.
What was your question actually?
No, yeah.
Is there a construction of
I told you this was, I was out here.
so just to recap, criticality is smallest thing that basically accompanies the P in your switching lemma. But this is why okay, that I mean this could have been defined in 1986 itself. Why is this an interesting definition? Because it actually implies a whole bunch of other things for the functions. So it implies a decision tree size for f itself before any restrictions are applied. It gives you a correlation bound. It gives you a switching lemma type of statement, but here there's degree instead of decision tree. So how much is the degree of the function drop when you apply the random testing? And then these are also some Fourier concentration. So that is why this is an interesting definition. So if for a class of functions, you can find the criticality, then you also get all of these results for free. And the one that we are most interested in was, of course, the second one, the correlation. But yeah, that is why this criticality is interesting.
Is it clear that there should always be such a lambda?
You can just say like 1 or something, then it's, or like 1 by p or something, then it's just
No, but you want it to be something different of P, I guess.
not be independent of p. I'm sure you can just put something that makes this just one property.
Criticality of parity is about it.
Criticality of yeah, because p you can't do it. Yeah.
Yeah.
Yeah, independent of p, I guess.
Maybe just the area.
And I think this,
So for switching lemma, what was the lambda thing there?
5 times 1 or 4 W. I think you can maybe make 5 into something else, but it's 4 W. Width of the data.
Width of the.
Yeah.
But here you want it to be a constant.
No, it will be something in the like the class of functions that you have. It will be something related to this. So, like our result is to do with AC0 circuits, right? So it's something in the size and depth of this. So this Harsha 2014 result, if you were to say it in terms of criticality, he basically showed that the criticality of AC0 circuits is this thing, log s to the d. And yeah, he this was via something called a multi-switching lemma, which I name drop again later. Okay, so we have finished one column of the second row as well, correlation one. So yeah, the question is what goes in the final box. So the intuition for why this might be, I mean, one silly way of looking at it is that, I mean, inside the 1 by d, like n is sort of getting replaced by n times d to the d. So similar to the circuit to formula blow up itself. So that's one reason for why this might be. So I mean, even if these quantities look a little mysterious, if you were to just say the if you were to just say the conjecture in terms of criticality only, and even if the circuit bounds thing, correlation bounds seem mysterious, so basically the conjecture is that for AC0 formulae, the criticality looks like this. So log s by d whole. So this was known already for regular formulae due to Rossmann in 1990. Regular just means that all gates at the same level have the same band. Yeah, I mean, you can't just convert this to this because that creates size. So,
when you say size, is the number of gates or the number of wires?
gates, right?
It's anyway with the logs, so probably doesn't matter. But like a
Typically, yes, it's just the number of bottom ands and odds. That's the the number of bottom ends and alls is good enough. Not even the number of waves. It will even
Or even number of leaves, I think some people.
no, not just leave. It will go one level over the number of ends and alls.
Since it's a log, it is kind of
These actually matter.
observed. 20. So this is our main result. Yes. The conjecture is true. This is the criticality of AC0 formulae. And yeah, like I mentioned earlier, this also gives us correlation bonds, Fourier transactions. That slide with all the implications of criticality is all of them are given. So this is our main result. This is the thing so far. So now I just give you three key ingredients in the proof. So the first one is something called a tree of random restriction. So if you remember what a random restriction is, it's just each variable independently. You just leave it unset or you set it to 1 or 0. So we define something called a tree of restrictions. So the tree basically has the same shape as the formula. So there is one restriction for each sub formula in the formula itself. And we wanted to have this property. So as you go up the tree, it's a further restriction, which is to say you set more and more variables as you go up the tree. They should be consistent with each other and you set more variables. So that's how these restrictions are all related. To give it a bit more detail, yeah. So if there's one restriction for each subformula, and if G1 is a subformula of G2, like this, then you want this to be a further restriction of the child. And these aren't arbitrary, so that we will keep it like this. So the top one is basically the main restriction that we are working with itself. And the internal formulae, we will set this as well. So this looks familiar. It is the thing in the criticality thing. This is the definition we use for analysis and also for defining canonical decisions. So if you have seen some proofs of Harsha's switching lemma, they use something called a canonical decision. So let me quickly recall what it is for Harsha's switching lemma. So for Harsha's switching lemma, it's on DNFs, right? So it's a term 1 or term 2 or like for each term, and each term is an AND. So how do they build a canonical decision tree for this? Basically, if all the variables are 0 or if it's at all. So if some term is 1, just make it 1. Leave aside those cases. Otherwise, you find a first term that isn't completely killed, which still has some variables that are living, and it's an AND. So the decision tree is exactly how you would expect it to look. You query 1, if it's a 0, stop. Query the next, until you have finished all of it. So this is kind of that looks like this. The thing on the left. That's just the decision tree for an AND. The canonical decision tree, how we make the optimal one into the canonical one, is just complete the tree. So even though you know it's a 0 spiritually, still continue to query all the other variables so that at the end you have a balanced tree and you query the same variables on every branch. So this has most of the branches will be 0, just the one branch will be 1. So this is for one term. And notice that every branch is also a restriction in a sense, right? Because you're setting variables as you go down the branch. So sort of apply this restriction that is a branch and then continue for each 0 leaf. If you reach a 1 leaf, you're done because it's an OR. If you reach a 0 leaf, then continue this process by applying whatever restriction you want to. So that's for the DNF case. For our case, it's pretty similar. So if you have some decision tree that looks like this, just complete it. Make sure you're querying all the variables in each branch. And we also define this association function thing. It's just for easier analysis. Formally, the CDT thing looks like this. So trivial cases, they're likely to come at the end when you set most of the variables. Otherwise, you find the first non-identically 0 subformula. Inductively build the CDT for that. Now remember that we are in a tree of restrictions, not in a single restriction. So when you've inductively built it, you've built it for the restriction corresponding to that subformula. So now that you're going up, remember that going up the tree is a further restriction. So you do up, so you might have to set more variables. You might have to trim some branches of the tree because they're irrelevant now, because you set those variables to some. And then you do the zero balancing, which I showed in the previous slide. And now, wherever you have zeros, continue the process. You sort of hang the subsequent terms. So that's our canonical decision tree. And why do we care about this? Because our main lemma is actually stated in terms of the canonical decision tree. We don't just say that the optimal decision tree collapses with high probability. We say that the canonical decision tree also is unlikely to have a long path. That's how we write it. So that is, I mean, in a sense, it's stronger than just saying that the optimal decision. The statement is about our definition of a canonical decision tree. There's one more way in which it's stronger, which is that we say that this row thing is not just some restriction. I mean, it could be drawn from the set of all restrictions, but we also say it could be drawn from any downward closed set of restrictions. So what does downward closed mean? What it sounds like. So a set of restrictions is downward closed if there is some restriction row in the set. If you take row and then you set more variables, that also continues to remain in this. So it's a similar definition that we just left for trees also. It's just node by node. And the reason why this helps, some intuition for why it helps, is that when we go about proving our main lemma, we are trying to bound the probability of this thing, right? That the depth of the CDT is at least t. So we write this as there is a long path in the canonical decision tree, and the way this looks is it's an OR of events which look like ants inside. So this OR is actually we want to say that there is some subformula that causes a long path to occur. So it's an OR over all of those. And inside when you write that there is a long path, then it looks like there is some set of unstarred variables and this happens and this happens. So this is how the event that we are trying to bound the probability of looks. And since it's an AND, you can write it just conditionally like this. So now it's a question of bounding this. And if AL, the event, also has a downward closure sort of property, then you can just use induction. So since, I mean, like I said, this thing is actually the formula, right? So this is sort of smaller formula, or maybe a smaller depth, or basically something that allows induction to take place. So that is why the downward closure helps. So it's a stronger theorem, but this condition actually helps. So yeah, so combining these ingredients with a heavy dose of Jensen in it, I think 3 times we use it. This is our main lemma, that the probability that the depth is at least t is most p times this criticality that we found, log s by d to the b times to the p, equivalently level. So just this is just a summary of the results, that we have a criticality bound for AC0 formulae. We have the switching lemma type of statement where this thing occurs, and also if a reduction and correlation bounds, we have a correlation bound between any f computed by an AC0 formula and parity. That's it. Thank you.
So it's equivalent to the conjecture, right?
Yeah, it proves it.
Yeah, are there any questions?